Deixa eu ver já está na hora. Podemos começar? Bom, eu vou falar em inglês, mas vocês podem me perguntar em português. Enfim, não tem nenhum problema. Okay, so the basic idea I want to talk about this conjecture, and the idea is that to make it as elementary as possible, like Fermat loss theorem. But it doesn't mean that if I introduce as elementary, you can solve it. Anyway, so I will not tell the status of the conjecture. The idea is that I want to go a little bit back in the history.
I don't know this conjecture.
Grothendieck conjecture.
Why you wrote Katz-Grothendieck?
Maybe later we discuss. F. So let's open F holomorphic. So once you do complex analysis, you have a lot of, you introduce the notion of holomorphic function. One of the things that you do it, you write the Taylor, you always write the Taylor series. I will write the Taylor series around Z0 equals to 0 in U, n equal to n at infinity. And so the basic one of the first challenges that when holomorphic functions are algebraic, F is called algebraic if there is polynomial in two variables. You can take it coefficients in C such that P, Z, and F as Z is 0. And okay, so the idea is that when we have this small class of holomorphic functions which satisfy polynomial equations, and have to detect algebraic functions among all holomorphic functions.
I think you want P to be non-zero.
Yeah, exactly. Okay. So maybe I first put a theorem. Well, and now the proof is easy, so it today must be called proposition, but it is due to the Eisenstein. Got I then. Then maybe I write also when they lived. This is he just lived 29 years, and 29 years old he died. But anyway, if F, so basically I will not need too much complex analysis. The language of the the formal power series would be enough for me. So if F is if you write the Taylor series, and it is has coefficients in Q, so this means that formal power series is in Z with coefficients in Q, and if is algebraic, so this means that there is a non-zero polynomial annihilating it, then, well, you can introduce it for ordered rings, but let's just have a rational number. So then there is n integer such that such that if you just multiply the argument by n, then actually this is integer coefficient. So what this means that at the end of the day, this fn, when you multiply by n, there is an n to the n, so there will be n to the n. This will be all integers. It is it is an easy proposition, but anyway, this is done almost 200 years ago. And, well, you will see that there is the first conclusion is that, let's say, corollary, the number of primes in the denominators of fn is limited. I mean, it is just the primes of n will appear in the denominator of fn. It's not. It is just a consequence, not equivalent, but only finite number of primes can appear in the denominators of fn's. And fn is an infinite sequence of rational numbers. Okay, so well, it's a kind of maybe another corollary. For example, is z or log 1 minus z are not algebraic. This is, and for example, in the case of ez is some zn n factorial, and n factorial always we have a lot. All the primes appears in the n factorial, so this means that at the end it doesn't satisfy even this weaker corollary of the theorem. So ez will not algebraic in the same way log 1 minus z. In the denominator of its coefficients, you can find all the prime numbers. So another thing that this theorem is not if and only if. I don't know what is the maybe observation. This theorem is not if and only if. Well, I was thinking what is the simplest example. In my course appears this Eisenstein series. Maybe I write it. Well, they are usually written in Q variable. It is something like this. Sigma n, Qn, n equal to m, infinity. Sigma n is the sum of divisors of, for example, this is also the same Eisenstein. Eisenstein series. And at the end of the day, all the coefficients are integer, but one can prove that Eisenstein series are not. There is EK also are not algebraic. Even so, all the coefficients of integers. I think there must be.
Much easier example.
Yeah.
You can use basic analysis, right?
Yeah.
Stats, just take a
Yeah.
sequence of integers, merging very fast.
Exactly. I mean, even the proof that they are not algebraic, it is not of these things is not so. You need a little bit to argument, but anyway, yeah, exactly. But anyway, so this is. But at least a good criterion to, whenever you have some transcendental function, to say that it is not algebraic. It doesn't give criterion to prove that it is algebraic. Okay, so well. Okay, so let me. Before going to to other things. So let me try to introduce the conjecture. So in this case, let's say we are interested in the solutions of linear differential equations. Linear differential equations. And well, so I don't assume that you need the language of linear differential equation, but let me write it. I will focus on just two examples. One example for computation, which the conjecture is true. The other one, that as far as I know, the conjecture is open. So let's take. So what is this? And I also will take just 2 by 2 matrices. y1, 1, y1, 2, y2, 1, y2, 2, yigs.
There's a question in the chat.
Huh?
There's a question in the chat.
Yeah, but maybe at the end.
Read that question. Already interrupted, so say the question.
What's an example of an algebraic function which is not the Taylor expansion of the rational function?
Square root.
1 plus z.
A square root of z plus 1. For it. Yeah, 1 plus z. Exactly. Anyway, okay. According to the literature, you find the Grothendieck cats because the people. But I think the main person for the conjecture is the cats. But anyway, let's. And okay, so let IYG holomorphic functions. Let's again take them from open set. So I am not interested at all the general context of the conjecture because even in a very simple example it is open. So I will take two examples. M either will be A divided by Z and denominator, or M will be A divided by Z plus B divided by Z minus 1. And this A and B, 2 times 2 constant matrices. So this is in order. I will use it in order to explain the relation with Kronecker's criterion. And at the end of the day, the conjecture is still open also for this class of differential equation. So I think to make it the conjecture more accessible to non-expert, I think this is also a good example to work out. And at the end of the day, you are interested on, I will write also in this format, usually rewrite as 2 by 1 matrices, but let me just write as this in this 2 by 2 format. You are interested in all these 4 holomorphic functions. And in this case, you, let's take, for example, for this example, C minus 0, 1. In the other case, just minus 0. And what? So you are interested in these 4 holomorphic functions such that when you make the derivation, so derivation is ddz. Then this is this 2 times 2 matrix, which is a rational function in Z, and then Y itself. And I don't want to. I will not talk about too much about linear differential equation, but something I want to say: any differential equation, at the end of the day, it is a recursion. If you write down the Taylor series of its solution, so let me write this. This is an easy proposition. Since already I have used the Z0 as a pole here, so I will write the Taylor series in a different point. So let's take Z0 minus 0, 1. If you want to, you can take a Z0 integer. There is a unique power series. So I will write the power series of this guy at Z0. So the power series will be in with coefficients which are matrices. Y, Yn, Yn, Z minus 0 to the n, n equal to 0, infinity, such that, well, it is the solution of your differential equation. And there is a unique, so, and I will put the initial term, just identity matrix. I think this is the best way to introduce the solution of differential equation without going too much to the context of differential equation. So, and actually the proof is very easy. So you just plug the formal power series there. So if you plug there, so y, so derivative of y is what is this? This is y1 plus 2 y2 z minus z0 plus, and there is a reason why I want to write this explicitly, z minus z0 n minus 1 plus so on. This is the derivation. This must be equal. Write down the Taylor series of this guy at z0. This is just a geometric series for both of them. So the Taylor series of this guy in z0 is easy to write. So maybe I don't want explicit example for these things. Cn z minus z0 to the n plus, and then times what? Times y0 plus yn z minus 0 yn z minus 0 to the n, and so on. So this is your differential equation written in the formal power series. And there's something, you will see that this is a recursion. So n, if you look the coefficients of z, coefficient of z, z0, n minus 1. So you will conclude that n, yn, and all these yi's are 2 by 2 matrices. N yi can be written in terms of y0, y1, and yn minus 1. And of course, this constant also you already know from here. So at the end of the day, you can compute the yn recursively in terms of the previous yi's. And why I reproduced everything here, and exactly this is because of this n. So once you want to compute yn, you have to divide over n. And at the end of the day, if you put in the computer and work everything, in nth step, almost you have divided over n factorial. In nth step, one has divided over n factorial. And if you start everything, for example, A, B, rational, and at the end you compute, and at the end you will get Taylor series with rational coefficients. So a priori, this means that you cannot apply Eisenstein criterion, because n factorial contains, when n grows, it contains all the primes. But the point is that it can happen for examples such that this n factor, the denominator, the primes in the denominator are cancelled with the denominators, and again you have a kind of finite number of primes appearing in the denominator. And after the simplification. So this argument will tell that in general the solution must not be algebraic, but there might be cases that the solution is algebraic. And well, this is if you look the literature, this is exactly one of the main difficulties that now I will tell the conjecture is that is this one, that when you look the solutions, you will see that in principle n factorial must pop up. Okay, maybe before introducing the conjecture, maybe I tell one example. Again, the historical example that the people tried to find the algebraic solution is the Schwarz, Hermann Schwarz. Maybe I write that. This is almost the mathematics of 19th century. Okay, so and I will not write the maybe. Basically, Schwarz example is this one. So you quit C minus 1. So you take A, B, C, any complex numbers. The matrix A and B will be very particular. It has a lot of zeros. Minus by 0, 0, 0, 0, A, C minus A minus B minus 1. Anyway, for the in this case, I will not write exact formula. Y can be written in the Y has 4 entries, but this I have to write exact formula. But in terms of Gauss hypergeometric function. And what is this? This is f a b c. The notation is this one. A n b n c n n factorial z to the n. N goes from n0 to the infinity. And what is this? A n. This will be appear soon again. A minus 1, a minus 2, a minus n plus 1. And so what Schwarz did, in this case, he classified. There is the Schwarz, called Schwarz list of A, B, C, such that the Y is a Y. The entries of Y, the entries of Y are algebraic. For example, if you put in Google Schwarz list, you will find this list. Maybe, well, I think it will not. It is a 15 class of A, B, C, and actually it is not. It's not difficult. It can be, if it is algebraic, you can prove that this IBC must be rational, and at the end of the day, this is in rational numbers. Okay, so I think this one I will not go into it. But what I'm saying, that historically, the people Schwarz classified just for this example, for which ABC, the entries of Y are algebraic. Maybe if you want, I put just one example from this list. Maybe, for example, A, B, C being 1, 2, 1, 3, and 1, 3, and so on. So there is a table. Okay, so well. The classification of algebraic solutions for arbitrary A and B metrics is still, as far as I know, it is open. And I just want to introduce this Katz-Grothendieck or Grothendieck Katz to this class. Okay, so any question? The conjecture Katz-Grothendieck for AB arbitrary. Yeah, with 2 poles. I mean, this one I will do a kind of use that exercise to get some information to show that the Katz-Grothendieck is true for this one and why it is a good exercise to do and how it is related to Kronecker. But for this one, still it is open. So let's go introduce the conjecture. And
Aren't they all equivalent to a hypergeometric?
no, these things, no, these are not all equivalent hypergeometric.
Rank 2?
Yeah.
Yeah, the function with 3 poles, so they are equivalent to some hypergeometric.
Maybe you write me the.
I think the hypergeometric.
No, okay, maybe.
General equation.
Okay, maybe. Well, anyway, if you put maybe n times n matrices, let me. As I said, I don't want to go what is done, but even maybe we discuss later. But for example, n times n constant metrics also. I don't know if somebody have solved it or not. As I said, I'm not going to tell what is the status. I want to say that if you write it for this class of differential equation, it's still have to say it's not easy to see why the conjecture must hold. And actually the thing, maybe you told me this. The things that 15 years ago I tried with my friend, exactly not these things, but these things with another pole, 1 minus zima plus c another, putting another pole, t and t another parameters, t not equal to 1 and 0. For this one, it is for sure it's completely open. But maybe. Well, I wanted to say if it is even if it is true for this class, if there is some elementary way, because for example this one you will see that how it is related to Kronecker. But anyway, let's discuss later. Okay, so if anyway. If this is going to be easy again, I don't know. But anyway, this one is still, but for sure it is completely open. If you put 3 terms, pole at 0, pole at 1, pole at t.
Georgie says that you need more technical conditions to have Schwarz this.
No, I know. This is up to permutations, up to some transformation and so on.
Not me, it's another George. It's the one that
I know. Exatamente. Okay, so.
O que acontece se a gente pegar N polos de ordem maior? Para dar um zero quadrado.
Well, you can do one of the things that it is proved that it is locally, if the hypothesis of the conjecture is true, locally always you can have the pole order 1. It must be Fuchsian, but this will be. I mean, you can write any matrix with rational entries, and actually the conjecture you can state for any matrix. But the hypothesis of the conjecture is very strong. It will imply a lot of things. Differential equation must be Fuchsian, very particular, and so on. So maybe. So this was our differential equation. So you start iterating n's derivative. So this is what? This is n's derivative. And at the end of the day, you can write this one as a matrix m times v, and you can compute this mn recursively, because when n plus if mn plus 1, why? So from another side, this is yn derivation. This is mn y. And at the end of the day, what is this? This is mn derivation of this guy, y plus mn y prime. And this is mn derivation mn m at the end y. And then you will conclude that mn plus 1, the matrix mn plus 1, it is m derivation of mn plus mn m. And what is the recursion? M1. M1 is the original m. Okay. So you can make the nth derivative, and so let's try to write down the conjecture. So for the statement, the conjecture. So let's take R. Now I will take the R, the Z module, generated by entries. You have this A, B, and if you write more matrices, or others. So this means that polynomials in the coefficients of A and B, these matrices, they might be algebraic, they might be rational numbers, and so on. And if you want, this will be Z sum n if AB has rational entries. So this will be the Z algebra generated by finite number of rational numbers. N will be the common denominator of all these rational numbers. So okay, so so let's try to write down the conjecture. Actually, the proposition, and then the converse of the proposition is the conjecture. Proposition. If the solutions of Y are algebra is the solution of the entries of Y are algebraic. So this way. And then there is something arithmetic happening. Then maybe first I write. So this M in the piece step, then for all primes except a finite number, all primes P. So you consider this MP. If you want to consider, let's say for this example with 2 singularities, 3 singularities, maybe just take A, B, C with rational coefficients. So in this ring, so you can do mod P, and in this case, let me fix on this example to write down explicit formula. So in this example, you will see that M. So the pole order of this Mn is n, because you are derivating and then you are where it is the criterion. You can prove that the pole order of Mn at at z equal to 1 is at most n. What I want to say, that at the end of the day, mn times, let's call this discriminant, delta to the n. And what is discriminant? Let's call discriminant the z minus 1. So delta n times mn will be a matrix 2 by 2 with coefficients in this ring. This is just by the recursion, because, and once you have, for example, in this case, when it has rational coefficient, then you can do mod p. Of course, you have to cut out the primes dividing this n. This is the first class of bad prime. So what I'm saying, that you can do this MP mod p must be 0, and this is the same. Well, if you want in another way to say another way, maybe you write in this way: delta n MP first multiply by delta n. So what is it? Delta mn will have pole order n at delta. Delta n mn will be just polynomials actually in z, because the denominator, you know what it is delta to the n. The numerator will be just rational polynomials in z with coefficients in r. And then what you say, that all these things that you get after mod p, they must be 0.
I don't understand why you want to multiply by delta n. They're just complicated.
Okay, maybe. I want to say to make it maybe let's.
Yeah, but it's still polynomial.
Maybe I will write m equals to 0 in, let's say, in R z 1 delta z model the p times z delta z. So in this ring, or if you want more, well, let me do this another version. Delta n mp, which is a matrix with whose entries are polynomial and z coefficient r. When you take mod p, this will be 0.
Delta p, right?
Oh, sorry, delta p. Okay, if you ask George, he will tell you immediately what is the proof. I mean, if you know the languages of, let's say, holomorphic foliations, I think the proof is not so difficult. But at some point, I started to try to find out a more elementary proof without going in too much to. I mean, elementary proof in the sense that just using, for example, using Eisenstein criterion. And well, I think it is not. It's an easy exercise, but really this one you can prove it. And actually, when you start to give a more algorithmic proof, you will see that really there are this, apart from these primes, which might appear in the denominators of your n in this ring, there might be other bad primes also. I mean, this is a good kind of good exercise. Okay, so this is the proposition, and then the conjecture is the other way around. No, maybe now that George complained, now I write it Grothendieck Katz. I'm a little bit, I don't know, I don't feel I don't know, I say I'm a kind of anti-Grothendieck. but anyway, I think they're really the Katz, the main responsible for, I mean, the main contribution really, I mean, all the work is done by Katz. I mean, it was a kind of observation by Grothendieck, but really Katz did all these works to see if the conjecture is true or not. But at the end, Grothendieck is God. He said that, okay, Grothendieck at IHES, he told him, I don't know, whatever. But anyway, so the conjecture is this one, the other way around.
You can also call Grothendieck Katz-Movasati, or even better, Movasati Grothendieck.
No, you are. Okay, so, well. My ego is not so high. You claim that my ego is too high. So the conjecture is the other way around, no? Then, so this. So if you have a differential equation for almost all primes, well, except a finite number, if this guy is modulo p is 0, then the solution must be algebraic. And as I said, well, I am still learning about this conjecture. Even so, 15 years ago, I wrote few things with my colleague Stefan Reiter trying to understand the conjecture, but really, as a systematic way, I started something like 6 months ago. I learned a lot of things from George. And if it is for two matrices, it is still solved, then at least for the other one, three constant matrix, it is open. So let's go to. So let's go to easy example, which will show that this has a lot of arithmetic involved. So let's just consider this differential equation. So this is what I'm saying, that the conjecture is very nice exercise in this case. And in order to not, I mean, even for A as a matrix, it is an easy exercise. But since I don't have time, let's just put a complex number. Of course, non-zero. And at least to say that this is related to Kronecker. So, well, for this one, even you don't need to.
What is the right arrow direction? Up there is to the right.
Huh?
One of the arrows should be the opposite direction.
So if the trees are algebraic, then this one and then the.
Yeah. So the arrow is.
So if for all almost all primes p.
He just wanted to explain the other side, so he changed that one.
I didn't want to do everything.
The correct proposition, the arrow is wrong for the correct proposition.
So this is.
Conjecture the arrows.
The conjecture is this one, from this guy. If MP is equal to 0 for almost all prime, then the solutions are algebraic.
Okay, but for the proposition, it's.
And for the proposition is the other way. If the solutions are algebraic, then for almost all primes, that happens. So maybe, well, this is called the P curvature. I will use this P curve. Okay. So, well, I think I will try just say this relation with Kronecker, and maybe let's say, okay. Okay, so very easy exercise. If you take nth derivative of this one, this will be a minus 1, a minus n plus 1, z to the n. Y. Actually, in this case, you have also, also the solution. No? This is just one function, a one complex number here, and this is just y must be of just type b, z to the a, b complex number, not equal to 0. No, there's a b, z to the a satisfies this differential equation. Well, z to the a, and also we know that this z to the a is algebraic function. This is the one, if you take, if I is irrational. I mean, this is, if take other complex number, these are not, okay. So, but this this doesn't solve the conjecture because it says that the p curvature must be 0. So let's do the exercise. So let's try to analyze the conjecture here in order to reach to this thing of Kronecker. So what was the conjecture? A minus 1, A minus plus 1. I will write it in a mod P format or whatever. Okay, so in this case, for example, you see that there is always z to the n, and at the end of the day, your mn is a. Okay, so remember then the Gauss hypergeometric function, we called it this a to the n. This is a n, z to the n, and okay. What is the hypothesis that the p curvature vanishes? Is that this is 0 in Z. The ring, the Z algebra generated by A, this is just, A must be algebraic, might be rational number, but in this case, you can consider this quotient by PZA. So if this is 0 in this ring, then the curvature will be 0. I'm just analyzing the hypothesis of p curvature being 0. So I put it px. Okay. First you observe that the a cannot be transcendental number, no? Because in order to see, so this is a. Let's write down this explicitly: a minus 1. A minus n plus 1. So this is P, some polynomial in QA. So the actual equality is this one, Q, a polynomial in Z, X, polynomial in one variable. So the p curvature is 0. That means that we must have this equation, and this is a polynomial in A. So this means that A must necessarily must be algebraic. Be an algebraic number. So even for one prime, such that the MP is 0, it will imply that M is algebraic. So I put it this capital P, Px be the minimal polynomial of A. So it is algebraic, so there is a polynomial in one variable of smallest degree which annihilates A. So I want to write down everything explicitly, but at the end of the day, what I'm saying that A minus 1, that A minus n plus 1. Okay, sorry. Now I'm mixing, so now I am everything as power prime. Sorry. Okay. So yeah, okay. So A. P plus P, some polynomial in. Huh? Okay, wait. P. It must be P. So that now write in a variable since this was a minimal polynomial. What I am saying, so there is an equation like this. Okay, so Px is the minimal polynomial of A. And with the hypothesis of p curvature equal to 0 implies that if you put instead of x a, it also it is a 0 of this way. Since px is the minimal polynomial, so px must divide any other polynomial which annihilates a. And here we are almost reaching to this Kronecker's criterion. presented in a different way without using number field and so on. So what we conclude, Px equal to 0.
It is minus P.
Huh? Okay, yeah. Well, it doesn't matter. Okay. So what we reach, Px equal to in Fp equal to 0 has, so let's call this one degree P equal D, has D solutions. So I have irreducible polynomial in one variable with z coefficient. When I make mod P, it has all the solutions, all D solutions. So, and this is for almost prime, prime, except I think this way is better. Finite number of P. So the problem is this one now. I have a polynomial, irreducible polynomial over integers, such that when I make mod P, it has the full, all the roots are there. And so maybe Kronecker. Maybe that again the same in the time of all these people, the 19th century, 1823. So the only possibility for Px to be just degree 1. Degree P must be 1. This means that the minimal polynomial is ax plus b. And n, m, and m integers. And this will at the end imply that a is a rational number. So the hypothesis of the P curvature of this guy is equal to 0 will imply that first, the I is not transcendent number, it must be algebraic number. And when you consider, you do this argument, you will see that its minimal polynomial splits completely over finite field. And actually, I have to look for an original article because all this concept of number field and so on appeared after Kronecker. But I think this polynomial version, it is also easy to understand. The polynomial who splits completely over for almost all primes except a finite number of them, it is just a linear polynomial which has one solution. And maybe, well, the thing that I wanted to, maybe just in 5 minutes and I finish it. I think I want to make observation again to something in number theory and to finish it. So maybe just this one.
Hossein, você não explicou por que P tem 10 soluções.
Modulo P, modulo P, this disappears. So Px has all roots just in 1 until P. I mean, is that right? So exactly, let me tell.
So D is smaller than P,
Yeah.
right? What are you saying?
Now what I'm saying that this equation, take it modulo P, this will disappear.
Okay.
And Px always divide x minus 1 until x minus p.
Modulo P, this becomes a product of linear polynomials.
The linear polynomial, exactly. So Px has, and at the end, Fp has just, what is Fp is just 0. Fp is 0, 1, and p minus 1. This means that Px, it has always the roots here. And you see that at the end of the, if even the degree of P is bigger, when you take the modulo P, its degree will decrease because the modulo P, it is a factor of this guy. So you see that there are a lot of things happening. Okay, maybe just the last thing I want to write in maybe in 2 minutes and finish it. I think this is, 3 months ago I was writing Georgie to clarify my ignorance, but I think this clarified my ignorance better. Okay, maybe I write this one, and then in number theory, in Gugu's talk, you will see something called Legendre symbol. I want to write this one, and to see that I think there are some arithmetic, more arithmetic going on. So if you have an integer and prime, you have something called the Legendre symbol. This is +1 or -1. +1 is when x2. So let's get D coprime with P. So this is a +1 if this has solution in FAP. X. P does not divide D. So Legendre symbol is +1 if this guy has solutions in FAP. Is modulo P as as solution has no solution. So this is the Legendre and so on. But the point is that you can write down this thing different with using differential equation, and there is a reason why I want to write this one. And P curvature of Y vanished. P curvature of what?
You cannot introduce new symbols. There is a D there. Is equal to D, no?
Where?
Or D is equal to A.
No. It is not. It's not. The D is actually. Okay, D is actually square root of D here. Sorry. Okay, I'm trying. So P curvature of this guy doesn't vanish. So the difference, D is integer, and now I am taking A, the square root of D. So the hypothesis that this has solutions, this means that it has two roots. It is the, if you follow that one, it's the same as the P curvature is here 0. And in this case, the P curvature is not 0. And a lot of people say that the whole number theory is just generalization of this reciprocity law. P, if you take two primes, P key odd primes, then P key, I want to write this one because I think it gives some hint. Maybe there are more arithmetic involved in the language of differential equation. So this is the reciprocity law apparently suggested by Euler-Legendre, but Gauss proved that gave the full proof. Now there are 1,000 proofs for this kind of this statement. But at the end of the day, what I am saying that maybe the last thing, and then go to the Y plane P Z mod Q. This thing has to do something with the Y plane. A square root of Q Z mod. No, it is Q and P. It's a kind of, I think it's kind of, I don't know. I think this kind of a correspondence between the differential equations of I'm not aware. But this means that at the end, if you can solve x to the 2 mod p here equal to q, this has to do with the same Diophantine equation, changing the role of the q and p. And this indicates that at the end, maybe, I mean, there are a lot of generalization of reciprocity law in the last 200 years. Well, what I'm saying, maybe there is something we can do also with reciprocity law in the differential equation context. I don't know, but this is, that's all. Okay, that's all. Now you can ask questions.
Any question?
Você enunciou a conjectura em termos daqueles equações diferenciais com dois polos só. Mas a conjectura é válida.
Não, uma conexão arbitrária. E na verdade, uma das consequências da conjectura que é do Katz, a conexão tem que ser forciana. E exatamente, tem várias consequências simples que o Katz mesmo elaborou, que realmente são as evidências mais fortes da conjectura vêm do trabalho de Katz.
Quais são as evidências mais fortes?
Bom, do Gauss-Manin, se p curvatura for zero, Katz demonstra para essa classe das equações diferenciais. Se no mesmo artigo, se p curvatura se p curvatura é sempre zero, então que a equação sempre tem polos regulares, é forciana. E esse de, por exemplo, bom, no meu contexto, se essas matrizes de resíduo em geral também, como que era? Eles têm R, diagonalizable with rational eigenvalues. Então, essas matrizes de resíduo sempre têm que ser diagonalizáveis. O bloco de Jordan deles não tem aquele 1, porque aquele 1 no bloco de Jordan produz logaritmo. E melhor ainda, os autovalores têm que ser racional. E esse também, de novo, os algébricos todos satisfazem isso. Equação diferencial cuja solução algébrica satisfaz. Os A e B são diagonalizáveis. E que mais? Tem o último de Mark Sin, com outro cara, aluno que tem alguns resultados, mas bota alguma condição bem forte na monodromia. Eu acho que vai ser inútil quando você quer aplicar num contexto explícito, porque você não conhece monodromia. Calcular monodromia é complicado. Se você quer... Não sei, Jorge, se você tem mais... Isso, acho que a mais forte é Gauss-Manin. Gauss-Manin, se P curvatura é zero, necessariamente as soluções são algébricas.
Okay, Federico, you can ask your question.
Hello. So if in Kronecker's theorem that you brought down, you replace except finitely many primes with infinitely many primes, is it still true?
No, exactly. This is exactly this example.
Hossein, your microphone.
Actually, 3 months ago, when I was trying to a little bit understand the things, George and Gregorio. Hey!
Já tô ficando doido.
Okay,
Technical
so
problems.
well, there are many examples. For example, George sent me a lot of examples of this issue of infinite number of primes, pre-curvature zero or not. But even this example shows already. You know that, for example, if you take a -1, a square root of -1, this is also for infinite number of prime, pre-curvature is zero. For other infinite number of prime, pre-curvature is not zero. So actually, this Legendre symbol, this example shows that this kind of things is. I think it is interesting because because of this reciprocity law. So not just focus on Katz-Grothendieck conjecture, but this kind of duality, I think this is also kind of a nice thing. Apparently, from arithmetic point of view, there is some duality. You can write down, I think you can write down this one explicitly for this differential equation and try to see if there is some generalization. But the answer to the example is just this, maybe put a equal to -1.
Any other
Thank you.
question?
Falando? Ok, então, agradeceu por me convidar mais uma vez. Ok, então encerramos a